Lesson 4 is part 2 of 3 on the topic of algebra, and algebra is our third of 10 major topics we're covering in the introduction to Shormann calculus. In this lesson, our focus will be more on true algebra, algebra, as we talked about in lesson 3, where we're working with linear equations, systems of equations, working with algebraic equations. So make sure you've looked at your rules and definitions first. Refer back to those during the lesson if you need to. But our focus here, like we said, is algebraic equations, especially the type that involve a ratio and or a rate, since that's what calculus is concerned with, ratios and rates, which we talked about in lesson 2. And calculus is mostly about two things: derivatives and integrals. If you understand what slope of a line is, then you actually understand half of calculus already. What that relates to the derivatives. So many of the problems in this lesson, they'll have connections to analytical geometry, which we'll cover in lessons 8 through 11. Our focus here is on just using fundamental algebra rules like the additive and multiplicative properties of equality to solve equations. If you don't remember what those are, go back and look at your rules if you haven't done that already. In calculus, we're applying calculus to things like algebra. So reviewing like we're doing here, that's just going to leave fewer questions, fewer areas of confusion for you when we do start to get into calculus in more detail. So let's start here with part A, linear equations. Look at example 4.1. Find the equation for the line passing through that point 2, 5 and having a slope of -1. So if you want to, you can graph this, and you could do the more analytical geometry type of aspect to it if that helps you think this through. But I'm assuming this is actually the 4th course for sure, probably the 5th course, where you've looked at equations of a line and slopes, first learning about them way back in pre-algebra. So hopefully all you need right now is just to remember y equals mx plus b. That's our standard form for an equation of a line. We use that as a template. We substitute the point that we've been given in 2, 5, and we know what the slope is. It's -1. So we can say 5 for y equals the slope of -1 times x is 2 plus b, and solve for b. Anytime you're asked to find the equation of a line, find m, find b, and you're done. So we know what m is. We were given that here. Now we just need to find b. We have a 5 equals -1 times 2. That's a -2. Move that over. In other words, add 2 to both sides. So this -2 will go away there. And so we get b equals 7. And therefore the equation that we are trying to find is y equals -1x, or just minus x is what we'd write there, plus 7. Moving on to example 2, we have two parts here. Find the equation for a line passing through this point, and A parallel to, then B perpendicular to that given equation, y equals 2x plus 38. So here what we're looking at is parallel lines. They have the same slope, right? Perpendicular lines, their slopes are negative reciprocals of each other. So in other words, like problem 1, we've been given what the slope is for both of these. We just need to find b for each. So for A, write our standard form down first, y equals mx plus b. Substitute in the given slope. For a parallel line, they have the same slope, so this one has a slope of 2. Also, y equals 2x plus b. Substitute the given point in now so we can solve for b. Be careful when you do this. Just because y is first, you don't put a -1 there. It's x comma y, -1 4. Y is 4. That's what we've been given. Equals 2 times -1 plus b. So let's just do mental math here. We know 4 equals -2. Move that over. So that would make it a plus 2. 4 plus 2 is 6. So b equals 6. And therefore our equation is y equals 2x plus 6. So same slope, just in a different location. A y-intercept of 6 instead of 38, like the given equation had. So b, first thing we want to think about is that the slope of this perpendicular line, it'll be a negative reciprocal of 2. So reciprocal means we flip it, right? So if the slope was 2, flip it. 2 over 1. We just think mentally, put a fraction, turn it into a fraction, 2 over 1. It's understood there's an over 1 there, right? That's just fundamental algebra thinking about a number, 2 over 1. So the reciprocal is 1 over 2. Negative reciprocal is minus half. So y equals mx plus by equals minus half times x plus b. And then substitute the given point in. 4 equals minus half times minus 1 plus b. You don't have to do it this way, but I'm going to think of this as decimals. So this would be 4 equals 0.5, a positive, because we have negative times negative is positive, plus b. So b is 4 minus 0.5, 3.5, and therefore y equals 0 minus 0.5x plus 3.5. So there's our perpendicular equation, perpendicular to y equals 2x plus 38, passing through that point. If you did this one in more of a fractional form, like y equals half x or minus half x plus 7 halves, I mean, that's fine. I just did decimal form. You should be able to distinguish between a decimal form and a fraction form and know that they would both be expressing the same thing. Problem 3, find the equation of the line passing through those 2 points that are given, 3, 6, and 1, 2, and write the equation in general form, not standard form this time, but general form, that ax plus by plus c equals 0 form. Recall Euclid's first postulate. That explains that all you need are 2 points to define a line. So we find it first in our standard form, y equals mx plus b. Find m, find b, and you're done, just like always. So here we haven't been given the slope, though we need to find the slope. The slope is rise over run, or change in y over change in x. So thinking about that, the difference in the y values, and looking at the right-hand one, that's a minus 2 minus the 6. That's our change in y, or difference in y's, over delta x, or change in x. 1 minus 3. So we end up with a minus 8 over a minus 2 equals 4. Our slope is 4. So we'd say over here, y equals 4x plus b. So we found the slope, now we just need to find b, and we're done. And we find b by substituting a point in, but we've been given 2 points. Which one do we use? Well, the line passes through those 2 points, right? So they're both on the line, which means it doesn't matter which one we use. I'm going to use 3, 6 because there's no negative signs to keep up with, which can always be a source of a careless mistake. So I'm just going to say 6 equals 4 times 3 plus b. 6 equals 12 plus b. Subtract 6 from both, or subtract 12 from both sides, we'd end up with b equals negative 6. And therefore y equals 4x minus 6. Now we're not done though, right? We were asked to find or write it in general form. So we need to move everything to the left, the x term first. And so we'd have minus 4x plus y. Move the negative 6 over to the left, that'd make it a plus 6 is equal to 0. Now, again, on a problem like this, if you wanted to have the x coefficient positive, you just multiply everything through by negative 1 on both sides, and that makes it a 4x minus y minus 6 equals 0 times negative 1 is just 0 again. So you could write it like that too. What you need to know, and this is something from algebra and pre-calculus also, should not be a new thing for you, but just recognizing that these two things are the same thing, and neither one of them is wrong. They're both general form. They're both okay. Let's move on to part B now, where we're going to review systems of equations, systems of linear equations here. So look at example 4.4. Solve that system. Write the answer as an ordered triple x comma y comma z. And note that the solutions are integers. So as you do the problem, if you get a decimal number or a fraction, then you're probably doing something wrong. So to solve systems of equations, which you should have done a lot of in your algebra and pre-calculus courses already, what you want to do is use substitution and elimination as necessary to solve them. And so we kind of scan through the three equations that have been given to us there, and we have the three unknowns. We look for things that might be the easiest to eliminate. So for example, if we added the top equation and the bottom equation, then we'd be able to eliminate y's right away, and then we could add two other equations, eliminate y's in them, and we'd have two equations in terms of x and z. Then we do substitution or elimination on those to get rid of another variable, solve for that one, then solve for the second one, then solve for the third. So here, let's just go ahead and rewrite one over the other one, x plus y minus 2z is equal to 16, and then that bottom equation, x minus y minus z, which means minus 1z, right, is equal to 7. Add those together. X plus x is 2x. Y minus y is nothing. Minus 2z minus z is minus 3z. And then adding 16 and 7, that's 23. Now, and there's different ways to solve these, of course, but I'm going to add the top and the middle equation. Multiply the top one, everything in it, by 10, so then I have a plus 10y, which I could add to the minus 10y in the middle equation and get rid of those. And so let's do that. X plus y minus 2z is equal to 16. Multiply everything there by 10, and so I'd have a 10x plus a 10y minus 20z is equal to 160. Now beneath that, let's write this middle equation, 5x minus 10y minus z is equal to 2. So add those together now. 15x minus 21z is equal to 162. Notice a common factor of 3 there. And remember, like on something like 162, if we add the digits up, 1 plus 6 plus 2, that's 9. And that's divisible by 3. Then the number is divisible by 3. So if you didn't know 162 is divisible by 3, which means it has a common factor of 3, that's one way you can do that. An elementary math skill there. But anyway, dividing everything by 3, we'd have a 5x minus 7z is equal to 162 divided by 3 is 54. Let's write that over here. 5x minus 7z is equal to 54. Now what could we eliminate? Well, we could eliminate the x's. Doesn't matter which one. I'll eliminate the x's here, and we can multiply everything in the top equation by 5, everything in the bottom equation by negative 2. Didn't have to do it this way though, right? And let's just do some mental math on that. So 5 times 2x is 10x, 5 times negative 2 is minus 10x, so we'd get a 0 there, and then we'd have minus 15z plus 14z. That would just give us a minus z, and then we'd have a 23 times 5 is 115. Adding to that, 54 times negative 2 would be a negative 108, so that would be a negative 7. So that means, just put a little arrow here, that means that z equals 7, right? Now we know z, we could substitute that into either one of the equations right above that and figure out what x is. And actually that's a minus 7 right there, right? Because we had the 23 times 5 is 115 minus 108. So minus z is positive 7, therefore z is negative 7. and we get 2x is equal to 23 minus 21 is 2. Therefore, x equals 1. Now, why don't we just substitute into this bottom equation, because it doesn't have any coefficients other than 1 there. That'll make it easy to figure out what y is. So we'd have 1 minus y minus a negative z is plus 7 equals 7. Minus y plus 8 equals 7. Move that over, we'd have minus y equals minus 8, or minus 1, because 7 minus 8 is negative 1, and therefore y equals 1. So x equals 1, y equals 1, z equals negative 7. We'll write that as an x, y, z ordered triple, and so we'll have here 1, comma, 1, comma, negative 7. So we had to be careful about some of those sign changes there. Maybe we should have showed a little bit more work on some of those, like here and here, but we were able to correct our mistakes. And another way to check your work, just to make sure that you're doing things right, is to substitute your solution set back in. I'll substitute it into that top equation, where we should have 1 plus y is 1 minus 2 times negative 7, which would be a positive 14. 1 plus 1 plus 14 is 16. That's what's on the right side, so that checks out. That confirms to us that we did that correctly. Moving on to part C on rational equations. With rational equations, meaning equations with a fraction, one or more fractions in them, get rid of the fractions first, either by cross-multiplying or by multiplying every term by the least common multiple of the denominator. So look at example 4.5. What do you see there as a least common multiple? It would be a 2 times delta x, right? So multiply every term by that first. And so on the left, that would cancel the 2's, and we'd be left with delta x is equal to 2 delta x times delta y over delta x, which means 2 delta y, and then plus 2x delta x. Think also just about what are we solving for. We're solving for delta x here, so that means all the delta x terms now, we want to get those on one side. So let's move everything to the left, and we'd have delta x minus 2x delta x is equal to 2 delta y. Factor out the delta x, because that's what we're solving for. Delta x, parentheses 1 minus 2x. Be careful on those. Don't just say, well, there's 2 delta x's there. I factor that out and I say delta x times minus 2x. Well, no, that doesn't work. You have to have that 1 right there. And think about y. Just expanding that back out, we'd have delta x times 1 is delta x, and then minus 2x delta x. So then write 2 delta y. Divide everything through by 1 minus 2x now, and delta x is equal to 2 delta y over 1 minus 2x. So there's our solution. Problem 6. We see ratios there, so we think get rid of fractions first. But when we have something we can expand, like multiplying that c by both terms inside parentheses, let's do that first. And so we could just rewrite this as y is equal to cx over 5 minus c times 3 over t. See, those c's would cancel, right? And we'd be left with a 3 over t. We're solving for t here. Just keep that in mind. Not super important right now. What we want to do right now is get rid of the fractions, which means we want to multiply everything on both sides by 5t. So on the left, we'd end up with 5ty after we expand this out, and then cx over 5 times 5t, that would give us cxt, and then minus 3 over t times 5t, that would give us a minus 15. isolate the terms with a t in them because we're solving for t. And there's different ways we can do that. We say 5ty minus cxt is equal to negative 15. Now, just thinking ahead, which is a good idea to do when you're solving a problem, thinking ahead, I'm going to end up with a negative fraction for my solution. I don't really want that, so I'm just going to reverse everything. And if I move the negative 15 to the left, I have a positive 15. If I move everything else over to the right, I'd have cxt minus 5ty. Do I have to do it this way? No. But on a problem like this, just be careful about thinking your solution is wrong if all it is, oh, I could just multiply above and below by negative 1 and I see my answer is the same as the solution is. So factoring out t now, we'd have 15 is equal to t, parentheses, cx minus 5y. And therefore t is equal to positive 15 over cx minus 5y. And that's it. Last part D here, let's look at word problems. And in word problems we have to be a little more creative than the other types of algebraic equations that we covered because you have to create the equation. There's so many types of word problems we could review. What we're going to do here is just review a few that are encountered in calculus, or forms of them are encountered in calculus. But you might also see these on like a standardized test like the SAT or the ACT. So some good practice here if you're still needing to take one of those types of exams, college entrance exam. So to solve word problems, it helps to organize your thoughts and consider 3 main points. And these work for any word problem, so these would be good things to write down. What is the problem asking me to solve for? What do I know? What are the key words or phrases in the problem? So look at example 7 here. What 2 positive numbers are those which are to one another in the ratio of 3 to 4 and whose product is 2028? So what's it asking me to solve for? 2 positive numbers. And I could just go ahead and call those like A and B. I may want to change that later, but I'll just say that for right now. And then what else do I know? Well, I know that to one another they're in the ratio of 3 to 4. I also know what their product equals. And then what are some key words? You know, in a word problem like this, we have to have the same number of equations as unknowns. So one thing we see there is that there's a ratio we've been given, so we could set up an equation for that. A product. Also, the numbers are positive, so that might be helpful information later. So those are some good keywords to make a note of and identify. So now let's just go ahead and try to start solving this. We know we need the same number of equations as unknowns. 2 positive numbers, their ratio is 3 to 4. So we could just say A over B equals 3 over 4. I could have said B over A equals 3 over 4. It doesn't matter what I picked. I'm just trying to find 2 numbers here. I also know their product, A times B, is 2028. So some things I could do here is I could rearrange the ratio. I could multiply both sides by B, and I could have A equals 3/4 B, and then I could substitute that in for A right there in the product equation. And then I'd have one equation, one unknown, so I could solve it for B. So I could say that 3/4 B times B would just be a B squared, right, is equal to 28. And then I could multiply both sides by 4/3 to get rid of that 3/4 on the left side. So do the math on that. You get B squared is equal to 2,704, which sounds like a really strange number, but now we want to take the square root of both sides and we could just solve for B that way, right? And we'd end up with, get your calculator out. Probably don't know what the square root of 2704 is off the top of your head, but it's just B is equal to 52, which means A is 2028 over 52, which is 39. So in this case, A is 39, B is 52. It doesn't really matter which one's which, so we could just say for our solution 39 and 52. This type of problem here is actually in Leonard Euler's book called Elements of Algebra, the book that most modern Algebra 1 and 2 courses are based off of. So he thought this was a good kind of game playing type of problem to get students to see how to create equations based on given information and understand what the story is telling them and how to set up equations to solve and find the unknowns. Notice also when we took the square root of both sides, we could have said that b equals plus or minus 52, right? And that's normally what you do when you take square root of both sides. You get two solutions. But what did the question ask? What two positive numbers? So we didn't need to be concerned with what the negative result was, the negative 52. We just wanted the positive number. And then we substituted that in to solve for a and get a positive 39. Problem 8, why don't you just take a minute and read that through and be thinking about the three main points that we consider in a word problem. So thinking about that, what is this asking me to solve for? Well, it's asking me to solve for each type of coin, coins of each type. How many? So a quantity of each type of coin. And what do we know? Well, we know there's 34 of them, but how many of each type is what we need to find out. We know how much the total is worth, and we also know that there's 3 times as many quarters as nickels. So some key words: the value of them, worth, each type. We want to find each type. And 3 times, so it's not 3 more quarters than nickels, 3 times as many. So that reminds us we need to set up a multiplication equation. We have 3 unknowns. That means we need 3 equations. Maybe you remember doing coin problems, and so normally we have one equation in terms of quantity, QTY I'll do for short there, one in terms of cost, and then a third equation in this particular problem. So the one in terms of quantity, we can use descriptive variables here: N for nickels plus D for dimes plus Q for quarters is equal to 34. This is the quantity, 34 of them. And then in terms of cost, well, a nickel cost 5 cents. So if you have 2 nickels, that's 5 times 2 is 10 cents. If you have N nickels, it's 5 times the number of nickels. So we say 5N. For dimes, dimes are 10 cents, so we say 10 times D. Quarters are 25 cents, so we say 25Q. And then this is in terms of cost. How much were they all worth? $5.80. On the left, we've been talking about things in terms of cents. So $5.80 is 580 cents. How many coins of each type if he had 3 times as many quarters as nickels? So 3 times as many quarters as nickels. Does that make sense? Well, think about it. If he has 3 times as many quarters, that means way more quarters. So if he had 2 quarters in our equation, we'd have 3 times 2 is 6 nickels. We have more nickels than quarters. That's not right. Think about this one. Be careful about that third equation. Q equals 3N is how we'd write that. Because now if he has 2 nickels, he'd have 3 times 2 is 6. He'd have 3 times as many quarters as nickels. So we could take that third equation there, substitute it in for quarters here and here, and then we get 2 equations and 2 unknowns, which we can break that down and solve it for either nickels or dimes. So substituting in 3N for Q in the quantity equation, we'd have N plus D plus 3N equals 34. And then in the cost equation, we'd have 5N plus 10D plus 25 times 3N, that would be 75N, is equal to 580. Adding like terms there, we'd have a 3n and an n is 4n plus d is equal to 34. So there's different things we can do here in the example problem in the reading assignment. I use elimination here, but we could use substitution as well. So I'll do it a little different here. I'll use substitution, and let's just solve for d here. D is equal to 34 minus 4n. And then we're going to have, in that cost equation, we'll have a 5n plus a 75n is 80n plus 10d. Well, d we're saying is 34 minus 4n is equal to 580. Now we have one equation and one unknown, and just writing that up here, we'll have 80n plus 10 times 34 is 340 minus 10 times 4n is minus 40n is equal to 580. And so we can add like terms there. 80n and 40n is 40n is equal to 580 minus 340 is 240. Divide both sides by 40. N equals 6. D equals 34 minus 4 times 6, which is 24. 34 minus 24 is 10. D equals 10. How about quarters? Quarters equals 3 times the number of nickels, 6. So that's 18. So we end up with, just use a different color here, we'll just say n equals 6. Just to summarize everything here, D equals 10. Q equals 18. And there we go. Let's do one more word problem, a rate problem, because rate is important in calculus. So just think about this. Willie could assemble 6 duck calls per hour. Jace, 9 duck calls every 2 hours. If Willie started working 1 hour before Jace, how long would it take them to assemble 100 duck calls? So the problem is asking us to solve for how long, right? It's asking us to find a time. And we know some rates there, Willie's rate, Jace's rate. We know they need to assemble 100 duck calls, that Willie started an hour before Jace, so there's quite a few things that we know there. So some key words: how long, assemble, what are they doing? They're making duck calls there. And 1 hour before is important there, so that we don't just say that they are working together the whole time. So what we can do is set up a rate times time equals number of assembled type of problem here. And so we'll say Willie's rate times time plus Jace's rate, and I'll say RJ for Jace, times time, they're working together here, equals, now I'm not going to say 100 there, because working together, they didn't assemble 100 duck calls because Willie started working 1 hour before. If Willie can assemble 6 duck calls per hour, just say 6 DC over hours times 1 hour, that means he assembled 6 duck calls on his own. So that means working together, they're doing 100 minus 6 is 94. So we have one equation there. It's got 3 unknowns, 3 variables, but we know Willie's rate. It's 6 duck calls per hour. We know Jace's rate, RJ, is equal to 9 duck calls every 2 hours, so 9 over 2. Duck calls per hour, just calls per hour, however you want to describe that. Now we can substitute in, solve for time. 6t plus 9 halves, or 4.5, I'll just put it in decimal form. 4.5t is equal to 94. 10.5 t is equal to 94. Divide both sides by 10.5. Just get your calculator out to do that. And you do need to do that. Don't just watch me write a number down. Get yours out. Check it. It's a way to cross-check me too, and just make sure I'm doing it the right way too. 8.96 hours. Now, that's how long it took them to assemble 94 duck calls. That's not how long it took them to assemble 100 duck calls. Be careful right here. We need to add the 1 hour that Willie worked by himself onto this, so the actual answer is 9.96. We were asked to round that to 1 decimal place, so that would just round up to 10.0. Don't forget units on this. Since it's asked how long, well, put the time down, round it to the right number of decimal points, and put the units, hours. 10.0 hours is how long it would take them. Okay, well that is all for lesson 4.